Good morning, everybody. Very good morning to the RECTV viewers. In this video, we are going to discuss about the different charge distributions and the electric field intensity due to different charge distributions and some numericals. Before going to the derivation of electric field intensity due to different charge distributions, let me explain you what are the charge densities. So for the three distributions, that is linear distribution, linear charge distribution, surface charge distribution and volume charge distribution, how we are going to define rho L, rho S and rho V. Now let me explain you what is rho L. Now if we take a simple wire, which is an example of a linear charge distribution containing a charge density rho L, and rho L is simply the linear charge density. That means it is defined as the total charge, let me say, is dq. So the charge contained in the wire is dq. So dq, and if let me say its length is some dl. So dq by dl will be the definition of rho L. So the linear charge density rho L is defined as charge per unit length of the distribution, and it is measured in coulombs per meter. Next, let me explain you what is surface charge density. Now let me explain, let me take a simple surface like this with an area of cross section of ds, okay, and it is containing a charge density of magnitude rho s, and let me say the area of cross section through which the distribution is there is ds. So rho s, which is the surface charge density, is defined as dq by ds. And what is this dq here? dq is the total amount of charge present in the distribution. Next, let me explain you what is meant by volume charge density. Now let me take the example of a box, okay, which is a three-dimensional element, and in this box, let me say a charge of dq, okay, a charge of dq is stored, and let me say its volume is dV. So how you define the volume charge density rho V? Rho V, the volume charge density, is defined as the total charge present in the volume divided by the volume of the distribution. So volume charge density rho V is defined as the total amount of charge present per unit volume of the distribution, and it is measured in coulomb per meter square. And rho S, the surface charge density, is measured in coulomb per, rho V is measured in coulomb per meter cube, and rho S is measured in coulomb per meter square, and this is the linear charge density is coulomb per meter. So for a linear charge density rho L, for a surface charge density rho S, and for a volume charge density rho V are the volume or the charge densities. So for the three distributions, we have got three charge densities. Now let us derive the electric field intensity due to a linear charge element. Now consider a wire or any line distribution, for example, along the z-axis. Now we are going to consider the cylindrical coordinate system for evaluating the electric field intensity due to a line charge. So first let us assume that the line charge carrying a density of rho L coulomb per meter is along the z-axis, and let me say the point P is the point where we are interested in determining the electric field intensity. So what is P? P is the point where we are interested in evaluating EFI. So point of evaluating EFI. And what is any point on z-axis? We can take any point on z-axis z, small z, where small z is the distance between the origin O and the point where we are considering on the z-axis. Okay, so P is the point where we are evaluating EFI, and Z is the distance between the point O and the point where we are interested in finding out where we are assuming the point on the distribution. Next, R, capital R is the distance between the point P and the point on the Z-axis. So now let us go for some small basics. Now, what is the position vector of this point A? Let me name this point as some A. So what is the position vector of AP? If you remember, if you observe, AP position vector is simply AP bar is position vector of P minus position vector of A. That is, what is the position vector of P? Since it is lying on the XY plane, since it is lying on the the horizontal plane, I need not consider the Z coordinate. So it is simply, I can write it as R into AR cap. Strictly speaking, it is R into AR cap plus phi into A phi cap. But phi into A phi cap we are going to neglect, because while integrating, all the phi terms cancel each other because it is varying from 0 to 2 pi. So for that reason we need not consider the phi terms here in evaluating the position vector of P. So the position vector of P is simply R into AR minus, what is the position vector of A? If you observe, since it is lying on the Z axis and that too at a distance of Z units from the origin, it is simply Z into AZ cap. Next, coming to the distance between point P and the distribution. What the distance between the point P and distribution is? If you observe capital R, it is R square plus Z square under root. Why it should be R square plus Z square under root? Because capital R is the distance between the point A and P. So its distance R can be simply under root of R square plus Z square. Next, let us evaluate dq. So what is dq? If you remember, since rho L is dq by dl, I can take it as rho L into, what is the length actually? Length is along the, since the length is along the Z axis, I will be considering a small length Z along the Z axis. So this small distance I can call it as dz. So rho L into dz would give us the value of dq. Now after getting all these basics, now let me apply the equation for EFI, that is electric field intensity. So what is EFI? DE actually basically the equation, if you observe, what is the basic equation? It is E is equals to Q by 4 pi epsilon naught into D square into A cap. This is the basic equation for electric field intensity E bar. Now I am evaluating first DE. So for DE it is simply DQ. So DE is DQ by 4 pi epsilon naught into D square into A cap. So now let us put each and every value here. So DQ can be replaced with rho L into dz by 4 pi epsilon naught into D square is R square plus Z square into, if you observe this, it is R AR cap minus Z AZ cap divided by under root of R square plus Z square. Okay, so in toto it is, now it is rho L into, now we have got two components, one is AR cap component and one is AZ cap component. Now we are evaluating DE. For getting E we need to integrate. So while integrating, if you observe, Z into dz would be taking a resultant of Z square by 2. So if I am evaluating any point from minus Z to plus Z on the Z axis, so the integral while substituting the limits, what it will be becoming, simply it is Z square by 2, okay, from let me say from some value of Z to minus Z to some value of Z. So what's going to happen, this integral after substituting the limits, it is going to become 0. So for that reason we need not consider this Z into AZ. So this ZAZ cap term can be neglected on the pretext that after integration it will be becoming 0 because of the substitution of the limits. So what are you now remaining with now? It is rho L into R dz by 4 pi epsilon naught into R square plus Z square to the power of 3 by 2. So suddenly how I got this 3 by 2? This is R square plus Z square raised to the power 1 by 2 and into R square plus Z square. So here it is 1 is exponent, here it is 1 by 2 is exponent. So while multiplying it is going to become 3 by 2. So effectively what are we remaining with now? Since we have neglected the Z component, I am remaining with D is equals to, I am remaining with the D bar strictly speaking is equals to rho L into R into dz into AR cap divided by 4 pi epsilon naught into R square plus Z square to raise it to the power of 3 by 2. Now we need to evaluate E by substituting the limits for Z. So from this I can get E is equals to integral. Now the variable of integration is dz, so which is varying from minus infinity to infinity, rho L into R into dz by 4 pi epsilon naught into R square plus Z square to the power of 3 by 2. Let us substitute Z equal to R tan theta. From this dz would be R secant square theta d theta, and when Z takes a value of plus infinity, so if I substitute Z with infinity, so theta takes a value of tan inverse infinity, so which is pi by 2, and of course we will write that also. At Z equals to infinity, theta is equals to pi by 2, and at Z equals to minus infinity, theta equals to minus pi by 2. Now let us substitute these limits of theta and let us evaluate E bar. So substituting these values of Z, what we get is integral minus pi by 2 to pi by 2, which is your variation of theta corresponding to variation of Z from minus infinity to plus infinity, rho L into R into, dz is simply R into secant square theta d theta divided by 4 pi epsilon naught into R square plus R square tan square theta to the power 3 by 2. Now let us segregate the terms. If I segregate the terms, the constant terms I can throw it. Rho L into R square by 4 pi epsilon naught into R cube. So all the terms which contains theta are inside the integral. So you are having minus pi by 2 to pi by 2. You have got secant square theta d theta divided by, it is simply if I take R square common, so you are remaining with what inside the bracket, R square into 1 plus tan square theta. So 1 plus tan square theta would be secant square theta, and secant square theta raised to the power 3 by 2 would be secant cube theta. So it will be secant cube theta. So 2 secant squares will be eliminated or cancelled, and you are remaining with what, 1 by secant theta. So if from the preliminary trigonometry identities, 1 by secant theta would be obviously cos theta. So you are having now integral rho L by 4 pi epsilon naught into, so 1 R also gets cancelled, so you are remaining with R into minus pi by 2 to pi by 2, 1 by secant theta would be simply cos theta d theta, and it is rho L by 4 pi epsilon naught. Of course we are forgetting AR cap here, so which is to be incorporated. So here it is AR cap. So rho L by 4 pi epsilon naught R into integral cos theta would be sin theta from minus pi by 2 to pi by 2, and into of course AR cap. So this turns out to be 2. So why? Because sin pi by 2 is 1 minus of sin minus pi by 2, which will give you 1 minus of minus 1 or 1 plus 1, which is 2. So you are having 2 here. So this 2 then gets cancelled, 2 pi, 2, 4, and you are remaining with 1, 2 in the denominator. So effectively it would be rho L by 2 pi epsilon naught R into AR cap. This is the final result of Relation for determining the electric field intensity due to a line charge carrying a density of rho L coulomb per meter. Now let us derive an expression for the electric field intensity due to an infinite sheet charge. Now sheet means surface. So let us consider a sheet charge containing a density of rho S coulomb per meter square lying in the horizontal plane or xy plane. Okay, so we need to assume that the sheet charge with rho S centimeter coulomb per meter square is lying in the xy plane. Now let us consider a small area ds on the surface area or the xy plane. Now this small surface area ds is lying on the xy plane. Since it is lying on the xy plane, the z coordinate can be taken as 0. Now let me evaluate ds. So what is ds here? The surface area. It is simply delta r into delta phi. Now we are taking the cylindrical coordinate system for our evaluation of EFI. Now ds, the surface area, is increments in r direction into increments in phi direction. So if you remember, if you recall from the concept of cylindrical coordinate systems, delta r is dr and delta phi is r into d phi. So in toto it is r dr d phi. Of course, since the area has got a unit vector, it is lying perpendicular to the z axis. So into az cap would be your area of cross section, area element ds. Now let us evaluate dq. So what is dq? dq would be simply rho s into ds from the concept of surface charge density. So rho s surface charge density is defined as dq by ds. So obviously dq would be rho s into ds. Now coming to the unit vector. So unit vector would be, now it is this point is the second point and this point is the first point. So this is now z phi, z into az cap is a position vector of this point, and here it is the unit vector r into ar cap. Okay, now we are not considering phi because while integrating the total, since it is varying from 0 to 2 pi, the components from 0 to pi would be cancelling the components from pi to 2 pi. So while integrating, all the phi components or all the phi terms would be cancelled. So for that reason we are not considering the phi components. So the position vector of the surface area is r into ar cap, and the position vector of the point on z axis would be z into az cap, and from this point to this point we are going to evaluate the element de. So now dE is given by, the basic formula for E is simply Q by 4 pi epsilon naught into R square. So based on that formula, dE would be, since we are considering the elemental electric field intensity, we need to consider the elemental charge dQ by 4 pi epsilon naught into R square into A cap. Now let us substitute with each and everything. So dQ I can replace it with rho s into ds into, ds I can replace it with r dr d phi. So it is r dr d phi into a phi cap into into a cap. A cap would be, since it is starting at this point, so a n cap would be r the second point minus the first point. So it is minus r a r cap plus z a z cap would be the position vector of this line. Now if I want the unit vector, just that divided it by under root of r square plus z square. So if I substitute here the unit vector is minus r a r cap plus z into a z cap plus z into az cap divided by under root of r square plus z square, and here it is 4 pi epsilon naught into, what is the distance? If you observe this distance, r square or d square is simply r square plus z square. Okay, so let us, for convenience, let us change it as d. So it is simply d square. So the distance is simply under root of r square plus z square. So we are having d square. So d square can be replaceable with r square plus z square. So in total, it is rho s into r dr into d phi into, here it is not a phi, it is az. So if I multiply the az into az, so you are having z into az cap. So this the dot product of az dot ar anyhow is going to become 0. So you are having 4 pi epsilon naught into r square plus z square raised to the power of 3 by 2. So this is dE. So from this, what is E? I can get integration. So if you observe this variables of integration, we have got phi and r. So phi varies from 0 to 2 pi in cylindrical coordinate system, and r varies from 0 to infinity because we are assuming that it is an infinite sheet charge. So you are having double integral, r varies from 0 to infinity and phi varies from 0 to 2 pi, and you are having the expression as rho s into r dr d phi into, of course, z, rho s into z into r into dr d phi divided by 4 pi epsilon naught into r square plus z square to the power of 3 by 2 into a z cap. So if you observe d phi from integral 0 to 2 pi, I can directly replace it as phi from 0 to 2 pi, which is having a value of 2 pi minus 0, which is 2 pi. So I can as well write this expression as, so let us get out all the constants. So rho s is a constant, 4 pi epsilon naught is a constant, and integral d phi from 0 to 2 pi would be giving a value of 2 pi. So here you are having rho s into z also is a constant, z divided by 4 pi epsilon naught into 2 pi. Here you have got 2 pi. So this 2 pi is signifying this 2 pi we got it because integral d phi from 0 to 2 pi will give you 2 pi. Integral 0 to infinity r dr divided by 4 pi epsilon naught into r square plus z square raised to the power of 3 by 2 into a n cap. E into a z cap. Okay. So now let us evaluate this, and for evaluating this definite integral, we will go for substitution method by putting r equals to z cos theta. Z tan theta. So if I put r equals to z tan theta, what would be dr? It is z into secant square theta d theta, and when theta takes a value, when r takes a value of 0, theta takes a value of 0, and when r takes a value of infinity, it will take a value of, theta will take a value of pi by 2. So why? Because tan inverse infinity is pi by 2. So that I can replace it with simply E is equals to rho s into, so 2 pi and 4 pi gets cancelled, you are having 2 here, rho s into z by 2 into integral 0 to pi by 2. So instead of 0 to infinity, it is 0 to pi by 2, and r I am replacing it with z tan theta into dr is z into secant square theta d theta divided by, you are having 2 epsilon naught here, you are having r square is z tan theta square. So r square plus z square, I can replace it with the z square into 1 plus tan square theta, which is secant square theta. So I can in total write it as z square secant square theta raised to the power of 3 by 2, and it is, so we have got z into z into z, 3z, so it is rho s into z cube divided by 2 epsilon naught into, we have got tan theta into secant square theta d theta divided by secant cube theta into, of course, z cube. So the z cube and z cube gets cancelled. So you have got from, of course, 0 to pi by 2. So the secant square theta and 1 secant theta will be remaining in the denominator. So tan theta by secant theta means sin theta by cos theta by 1 by cos theta. So c gets cancelled, so you are remaining with sin theta. So this total term inside the integral will be reducing to sin theta. So you are having rho s by 2 epsilon naught into integral 0 to pi by 2 sin theta d theta, and if you observe this integral 0 to pi by 2 sin theta will reduce to 1. So it is simply, of course, we are forgetting az cap everywhere. So it is az cap here, az cap here, az cap here. So here it is rho s by 2 epsilon naught into az cap. So what I mean to say is finally we got the electric field intensity as rho s by 2 epsilon naught into az. So if the sheet charge is lying in the ground plane, the electric field intensity will be in that direction which is perpendicular to the plane containing the sheet charge. That is, if the sheet charge is along xy plane, so E will be in the z direction. If the sheet charge is along zx plane, the electric field intensity will be in the perpendicular direction of the sheet charge, which is y direction. So if it is in xy, the E will be in z. If sheet charge is in yz, the electric field will be in x direction. Like that, the sheet charge in whichever plane it is there, in the perpendicular direction to that plane containing the sheet charge, you will be getting the electric field intensity. And the magnitude of the electric field intensity is given by rho s by 2 epsilon naught. So one thing you should remember here, in the electric field intensity due to the line charge, we are having a distance in the denominator. But coming to electric field intensity due to a sheet charge, there is no dependency of the final value on the distance. So due to this, we can say that electric field intensity due to a line charge is dependent on the distance between the line charge and the point where we are interested in determining electric field intensity. And coming to the electric field intensity due to the sheet charge, there won't be any distance dependence in the final results. Okay, so in the next video we are going to do some of the problems on electric field intensity due to line charge, sheet charge and point charge. So if you have got any doubts regarding this topic, please feel free to comment in the comment box. And if you like this lecture, please try to subscribe to our channel RECTV Education. Thank you for watching.